balls. Now it's just one ball, not two. The ball is initially at the position start row comma start column. So just a quick glance that I will be given m comma n. M is the number of rows, n is the number of columns. It's a matrix, and I will be given start row and start column. Okay, this is 0 comma 0. From where, in what point of the matrix I am starting off? It's a 0 comma 0. Great. Now it also says one variable as maximum number of moves, that how many maximum number of moves I can actually do. So what it mean and what he wants from that maximum moves, he want that, okay, I'm allowed to move the ball to one of the 4 adjacent cells, which means if I am, let's say, if this is a matrix, I am at this cell, in one move I can either move to up, right, left or down. This is a 4 possible options for me to move my ball, and also I can move out of the grid also. Cool. Now you can apply at most maximum number of moves to the ball, which means maximum moves is the limit, which means I can apply these number of moves to my ball. And we have given these integers, which I have already showed you. We have to return the number of paths to move the ball out of the grid boundary. We have to return the number of paths to move the ball. Again, I want the number of paths. My ultimate aim is to move the ball out of the grid boundary. For that, I want to find the number of paths, and for sure it can be very large. So give me modulo 1 to 7. Let's see the example statement, what he wants. Okay, moves are 2. We saw it's a 2 cross 2 grid and starting from 0 comma 0. So I start off from this cell. In one move, I can go up, left, right or down. As I go up or left, I will go out of my grid, and that's what he wanted. So there are two ways. Okay, when I was starting from here itself, there are 2 ways to actually go out of my grid. So I'll increase my answer by 2. Okay, my answer is because number of paths will actually increase by 2. Okay, now in the next move, for sure it will, if it has gone out, it can never come back. It's not okay, I'll go out and then come back and then first go out. No, we'll just only go out. Okay, that's it, ball is gone out of the matrix. Now for the possibilities, when the ball is inside the matrix, okay, ball could be gone on the right side or it had gone on the down. Okay, if it gone on the right side, again it is the, okay, in the one move it has gone right. Now in the second move he can go up, right, left or down, but Aryan, left was already visited. I want paths, which means let's imagine your ball again. I'm just tracing one path for my ball. So my ball can go this. So you saw my ball is tracing a path itself. So it is a path, which means you can see if I go left, I can also come right also. Don't confuse it with the BFS. Okay, if I have visited a cell, I will not visit that again. It's a path, which means if I go like this, okay, now see, you were actually here. Your number of paths, your number of moves were actually, okay, 2. So like, okay, right now I can do one move and then I can do another move. So as you went here, that, which means, okay, you were starting here, then you right, and then you came left, and then you could have come down also. So right, left, down, it's one path, and okay, from this ball down, it's one path. So there are 2 paths for it. So okay, even if I have gone through that, I'll still can visit back. So I can also go backwards, then down, and then for sure right and up. Now right and up is just another 2 moves, for sure, sorry, another 2 paths for me to go out. Okay, I'll add 2 in my answer. And the other possibility we saw, that if it had gone down, again I will have 2 outs. So I will have, okay, it can go out, 2 outs. Now your number of moves are exhausted because you have, okay, one move was done coming here, another move you have done, okay, either going out or down, which means in the next move, for him, after he has completed his second move, he would be either out or on these cells. That's it. Now again, after it is, your question is done. So you saw that you were able to achieve 6 out paths, which means the path which in 2 moves, at max 2 moves, the number of paths from which I can actually reach out. So it's 6. Now let's see with the super, again, by this example itself, you could have actually figured out that what can happen. So in as simple as that, if we plot it, so we saw that we were at one point and we had 2 options. Like all we have 4 options. We can go right, down, left, or up. And as I go out, I know, okay, that is one path for me, one valid path for me. As I go out, again, in early cases, you were seeing, okay, as I go out, it's not a valid path. But for the question here, right here, as I go out, it's a valid path. Okay, great. Now, what if my moves are exhausted? Okay, as soon as my moves are exhausted, I'll simply say, okay, that is completely done. Which means, in the example, as you saw earlier, if your moves are exhausted, which means if your remaining moves become 0, which will become 0 after this operation, so you can easily say you have to return a 0 itself, because there are no valid moves remaining. So for sure there will be no paths also for that move. And ultimately, what all options we have? We have 4 options. If I am standing at I and j, this is I comma j, I can move to I plus 1 comma j, I can move to I minus 1 comma j, I can move to I comma j plus 1, and I can move to I comma j minus 1. These are the 4 options which I have. I simply try all these 4 options. So my code looks as simple as that. If I reach out, which means my I is m, my j is n, I less than 0, j is less than 0, which means I'm out of my grid, then I'll simply return a 1, because that's a one valid path. And for sure, as we saw, if my remaining moves, although maximum moves is the moves which you have remaining, if this becomes 0, simply return a 0. And for sure, you can try recursively for all the possible cases. Okay, you can try to go to I minus 1 comma j, I plus 1 comma j, I comma j plus 1, and I comma j minus 1. These are 4 options which you can try. Now, if we see off that's okay, for one ball at a location, I have 4 options. Now to figure out, although from here itself you can figure the time complexity out, but for just a general case, without even writing the code, if you want to figure out the complexity, it's nothing but, okay, if for a one ball you have 4 options, and it will keep on going, it will keep on having 4 options for the entire tree. Of what depth? Of the depth number of moves, because I was doing, okay, this I have 4 options for one move. Now as soon as the ball reaches at these points, again for all these balls which are this and this, I will again have 4 options, because of 4 directions, right? 4 is the directions, and this was, okay, one move. Now next move again. So at every move I have 4 options. So 4 raised to the power maximum number of moves is the complexity, is for the time complexity for us. And for sure the depth, entire tree depth, is maximum number of moves, which will for sure not work. 4 raised to the power 50, it will never work. So you are screwed up. No, you are not. If we see and look back, for sure it's a recursion. Maybe we can memoize, but we have to prove that it can be memoized. So what we could do is, okay, if we were at this cell, let's imagine we were at cell 0,0. Number of moves remaining are 5. Okay, now as soon as again it can go out, I can increase my answer by 1. But if it stays in, okay, one option is it came down, which means this cell. One option is it came right, which means this cell. Again, he is now at cell 1,0. Now the possibility, or basically the number of moves remaining for him, is 4. Now if he is at this cell, again he is at 0,1, number of moves remaining are 4. Again, when he can go up, so answer will increase by 1. He can go left, answer will increase by 1. But still, he has all these 3 options again open to him. So again, for 3 options, again I could not write all 3 because of the space. But if I just show you 2 options, so okay, it is up, it is right, it is down. So okay, I can say up 1 I wrote here, right 1 I wrote here, down 1, you can just imagine there will be one move 1 which is down 1. Same way for this, it can be right, down, and left. Same way, I could not write all 3, but yeah, I'll just show you that for for this left one, okay, I want to have at this cell, yeah. So I will be having that, okay, left 1, this is 1, down 1, which is this is 1, and right 1 will also be there. Now if I just again come back and ask you, now it is a new problem saying you are starting from 0,0, number of moves, maximum number of moves remaining for you is 3. Same 1,1, maximum number of moves remaining for you is 3. Same 1,1, maximum number of moves remaining for you is 3. And same 0,0, maximum number. So you will see This is the two same sub problem for which you are calling the recursion again. So for both of them, the entire recursive tree will keep on iterating again and again. So rather, you can just memoize that. Now, memoizing is simply nothing but you know that you have I, J, and all, and your this remaining number of moves. So you need to have these three states, because these are states on which your entire tree is actually built, right? From this number of moves remaining, from this coordinate number of moves remaining. So your coordinate I, J, and number of moves remaining is actually the states of your DP. So I'll simply do the exact same thing which I showed above. It's just that I'll now memoize that. So I have initialized globally my 3D DP. I know because one state is M, other state is N, other state is my max number of moves. That is my state of my DP. I initialized my entire DP with a value of -1. Now I can simply go and solve a simple recursive function, solve from this specific start index. Again, this here it was the start, and if you remembered in the basic code earlier, we had these, like we had the start. Okay, I'll start from I comma j, although the variable in the question is something else, but you're actually using I and j, so it's much more easier. So yeah, you will start off from I comma j, thus you pass. Okay, I have started from I comma j, and my number of moves remaining are maximum number of moves. Now simple recursion, the exact same base condition. If you reach out of the grid, which means if I is M, J is N, I is less than 0, J is less than 0, simply return a 1, because that's a one possible path. If your remaining moves become 0, simply return a 0. This is a simple memoized step, that okay, DP of I, J, and remaining moves, if it is not equal to -1, then simply return that DP state value which you have stored. This is the exact same. Again, make sure to do a modulo, because the problem was saying for the modulo also. So I just simply did a modulo also at every step. That is a basic operation, but exact same thing. I plus 1 comma j, I minus 1 comma j, I comma j plus 1, I comma j minus 1, with the remaining moves are decreased because one move I have done above, and simply store that in your DP. And that's how, by simple converting, or basically simply adding these two conditions, this and this return condition, you have simply memoized that and simply return the answer. Now you know your DP state have simple I, J, and remaining moves, so your complexity will also be M, N, and remaining number of moves, which is the maximum number of moves, and space also is same. Now okay, that up till so far, although I'll say up till so far it's a medium problem because it's a very standard DP problem, but now I'll ask you, can you improvise that? Earlier, so far, improvisation in DP we had seen only in a 2D DP, where you had just I and J, and it was very easy to visualize also. But now I am saying, can you improvise that? Now it's a 3D DP. You know that you have to convert that 3D DP to a bottom-up DP. And that's actually going to be tricky. But again, we will see that. Firstly, converting that to bottom-up, and then we will see that how we can improvise that. So now, to convert the same thing to bottom up, we will actually have to trace back the same example. Again, you might see Aryan in many videos, we see that it's very easy to convert from top down to bottom up. Yeah, it is true. But in some problems, you cannot directly convert your top down to bottom up. So you have to figure out again, because see, right now you will just see that you are accessing all these. So you are trying to have remaining moves. From remaining moves -1, you are actually trying to grab that value. So we will try to do the same thing. We will try to find the answer for remaining moves +1 from remaining moves. That's as simple as that, because here it was moves -1. So I simply said, okay, remaining moves +1 and remaining moves. I'll try to do the same thing. Again, whenever you are converting to bottom up, make sure that you take the reference of top down parallelly, right? Okay, cool. But your base case will change, because you know that you cannot go out in actually a grid, because it's a bottom up. So it's a matrix. You cannot go out. It's not a recursive case that it will try to go out, and then you can also handle that. But yeah, you will have to handle that. If I am inside, like before going out itself, I know, okay, now at this point I could have gone out. So before going that, which means if I am at the borders, then I know in the next move, I know, okay, I am at these borders, at these location. So I know for sure in the current move, I have a possibility to go out. So I'll use that knowledge which I have that, okay, if I'm at the border, I can go out, rather than actually going out of my matrix and placing if conditions. I will actually say, if I am at the border, I know that I could have gone out. So if I am at the border, I could have gone out like this, 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 and like this. These are the possibilities for me to go out. I'll just handle these possibilities at the border itself. Now let's see that how we can do it. So again, firstly, if I am starting from, again, we'll just trace back and see, but we know that our rough structure will look something like this only, right? If we have a remaining move, we will be accessing remaining move -1. But as I mentioned, I will be doing a remaining move +1 here because it's a one indexed, right? Because I have made my DP one indexed to actually make my, you'll understand. But yeah, it's remaining move +1 and it's remaining move, right? Okay, cool, no worries. Let's come back. Now we just trace back a little bit, that if I'm standing here, firstly, I will initialize something. I have to initialize my DP. As you saw, in a base case, you usually initialize your DP with something, initial values of DP. Usually you show the 0 values by default, but something itself needs to be initialized. We don't know what that gonna be. And also I know that I know I'm currently at i, j, and the remaining number of moves are 5 for me. But you saw, you are building bottom up. So I'll say, okay, I'm currently at the first move which I can perform. That is okay, because I'm building bottom up. So I'll go, okay, from move 1, then move 2, then move 3, and so on and so forth. Now, if I am, firstly, I was starting from 0, 0. I am actually at the borders. How I know? How I know I am at the border? To simply know if you are at the border or not, that your I, is it a 0? Your I, is it a, again, m-1? Your j, is it a 0? Your j, is it a n-1? If any of this case is there, which means you are at the border. Now again, for the same case, okay, you will see, okay, my I is actually a 0. So which means I am at, I will have one of the outs, which means I can go out in one directions. And I saw my j is also 0, which means I can go out in other direction also. Okay, I know that from this base, from this cell, I can go out in two directions. But right now you just saw that I'm just saying I can go out in just 2 directions. That's it for this cell only, because it's a first move which I'm having. Again, that can be confusing because we gonna see a 3D DP bottom up approach, which actually is tricky. So please be with me. Again, it's not a medium, considering you actually go on to bottom up, and people don't go because it's actually tricky to make you understand and to understand also. Now, but as we go on to next state, which is the move 2, what will happen? We will have to, again, in move 2, I need to know that in how many ways I can reach to, okay, if I am reaching to this specific point, I know, I remember that, okay, from move 1, I can go out, that is obvious, but I can also go to move, I can also go to some other cells, which is this cell, So I have to make sure in how many ways I can come here. Now it is obviously that, okay, in move 2, in just one number of way you can come here, and that is from above. Now Aryan, why is that even needed? Why you want to know the count of number of ways to come to this location? It is because that if you remember that you can come here either via up or via right. How? If you are in the, again, in the move, in the second move, you were at this, after the first move, which means at the second move, you are about to do the second move, you were at this location. Now when you were about to do the second move, you were at this location, right? If you can see the tree, that is like this. Now you know that after this second move, which means in the third move, he can go here. In the third move, he can go here, which means to come at this specific cell, as I showed you, repeating the problem, I have 2 ways. Now how that 2 is useful is, what if, now this 2 represents that to reach here in the third move, I have 2 ways. Now if you remember, I wanted to know ultimate maqsad is to find the count of path. I'm saying what if this specific value, let's say dp of I comma j, right, if this would have been a 2, as we have shown here. Now what this 2 would have said, again I'm just saying hypothetically, let's say if this would have been a 2, hypothetically it would say that to reach here in third move I have 2 ways. To reach here in third move I have 2 ways. That can be any 2 ways, and that I am kind of adding up from my parents, which is from the second move he will propagate the value and say that from me I can give 1 move to my child. So this will give 1 possibility to his child, which is this specific value. This parent will give 1 possibility to his child, which is this specific value. So he will give 1, saying okay, 1 move you can take from me. He will give 1 move you can take from me. So he has got 2 moves. Now I am saying that I can reach at this specific cell in 2 ways. Now what will be the answer which he will contribute? If it is just okay, if as you remembered he contributed only 1 and 1, so I incremented my answer. Okay, number of paths were actually 2, but now if I know I can reach here in 2 ways, so one of the ones will give 2 and other path will give me other 2 ways. So in total my answer will be nothing but 2, the like number of ways, which is 2, into the actual path, which is 2. So I can easily say that for I know number of ways, so number of ways to actually reach at this point, at this last point, let me change the color, to reach at this last point is 2. So to go left I will have 2 paths, because the number of ways to reach here were 2. To go right I will have 2 paths, because number of ways to reach here were 2. So this will help me to give the count of actual paths. Now coming on back again, if you have not understood this, please plot this and I'll repeat once again for the folks who have actually got this. You can skip this part, but I'll repeat once again very concisely how actually it happens. So initially in the very beginning I will populate my base value, which means the base case, saying dp of 0, 0, first move is a 1. Why I said that is 0, 0 is a starting point, and for after, like, it is a first move which I'm about to do. Now number of ways to reach here is just 1. This is what this dp state represents. That starting point is this 0, 0. It is a first move which is I'm about to do, and number of ways to reach here is just 1, because it's a starting point. So I will be standing here only. Now what will happen is that I will ask him that what is your cell? My cell is I comma j. Let's say in the code I will say it as x comma y, right? Now my cell is x comma y. I will say check, okay, if x is a 0, if x is a 0, x is a n minus 1, sorry, x is a m minus 1, y is a 0, y is a n minus 1, n minus 1. If x is 0, which means he can contribute by going left outside. If x equal to m minus 1, in down, it is in up, it is in down, he can contribute by going on the left side, in the left side, left, down, and same goes for right. He can also go right, because it's just one corner, right? You saw one can have at max 2 values, left, right, and all that stuff. So just going out, I'm saying now, and same goes for him. For up, like for this 0, I can go up, I can go down, and same goes for this, that for this 0, he can actually, like for this specific 0, he can go up and down. So just representing that I can go out for every of these possibilities, right? For every of these possibilities I can go out, as I showed you. Up, left, down, right, down, right, up. So this is, I'm just representing that I can go in these directions. Coming on back, I will say that in my first move, I know number of ways to reach here is 1. So outside or above, I can go in one way only. Outside, I can go in one way only. But I need to also give my child that in how many ways my child could be reaching. So I will say, okay, firstly, I got the answer which I wanted to have. Then I will say for my for my other child, which means for my 4 possible childs, again for my four possible childs, here I have only 2 because of right and down. So I'll say, okay, you could, in the next move, you could be reaching one way, and I'll also say to him he can also reach one way. So this value, which means dp of 1 0, in the second move will actually be storing 1, saying that 1 0 in second move I could reach in one way possible. Here also dp of 0 1 2 will say it's a one way possible. And again, before propagating the values to the child, I will have to compute the answer for me as a current path, which means how much I can contribute to the path, number of possible paths. So I will just say, okay, my I is actually nothing but 0. Sorry, my j is nothing but 0, which means I am at this specific left border, which means I can only go out. I can only go out left like this. So for sure, if I can go only out, so I can contribute my answer with nothing but, again, that is nothing but I'm contributing my answer with these number of ways, which is dp of 1 0 2. Again, I added 1 only in the answer, but this is nothing but number of ways to reach here, because number of ways to reach here, that means number of ways I can also go out. And the same way I'll add my answer. This one is nothing but this specific value itself. This specific value itself will get more clear when you will see that when he has added in the answer, he will again give his childs that, okay, you can reach here in me ways plus one way. Okay, I have just one way to reach. Okay, for sure you can reach here, okay, in these many ways. You can reach here in one way. You can reach here in one way and one way. Now he can say that I can reach here in my third move. I can reach here. Again, when I say third move, I am saying I am about to do a third move. I can reach here in 2 ways. Now if I just represent that as a edge value, which means let's say it would have been at edge, like super edge, so as maybe it might have been contributed to the answer. So it say, okay, I can reach here in 2 ways. So for sure I can go, because again I have options to say that I can go left, I can go right. So I'll say that 2 ways I can reach at this point. So for sure 2 ways will be outside also, and 2 ways will be down also, like outside right, like outside left, and outside down also. 2 ways will be there because my value was 2. So in my path answer, I'll be saying answer plus path. Now path will be nothing but dp of ij, and again like move will also be a like value, but answer will be nothing but contributing to the dp of ij. But for all of them, like I'll just say check if I equal to 0, I equal to m minus 1, j equal to 0, j equal to m minus 1, because you saw depending upon what point it is, although you can also add if conditions, many other if conditions, but as I showed you, I can have all these possibilities to go out. So I have to handle all those possibilities. Now let's see the code again. If you have not understood that, I'll say can you please go back and draw it by yourself a bit more example, because again it's a 3D DP bottom up, which can be tricky for you. Cool. Now the code is as simple as that, as we explained, that firstly we'll initialize, our DP will remain exactly same. It's just that by default value should not be a 0. Now Aryan, why is this maximum value plus 2? Because you remembered I was saying that for my DP of, again this I have taken it as a x comma y rather than I comma j, because if you remembered my I comma j was my variable itself, so I was thinking, okay, let's take x comma y itself. So although I could have modified this to the original start point, start x coordinate, start y coordinate, and then would have used I comma j, but I was very lazy for this, so I just took as x comma y. Now coming on back, we'll simply do, okay, I'll go on to all my moves starting from move 1 up till the last move, maximum number of moves, because you know I was doing, okay, first move, second move, third move, like this, and then for every move I will have to go into the entire matrix. Now before propagating the value to my child, I will have to first contribute, I will have to first find the answer which I can contribute in my path. Base case, as I mentioned, this is a start index, and the first move I will say I will contribute 1. Now before even starting off, which means propagating the value to my child, I know every node will have 4 childs. I will say that can you please contribute the answer which I can give? So these are the 4 cases which I showed you, that corner cases, like the, okay, how the answer can only be contributed if you are at the borders of the matrix. So this is the borders of the matrix, right? And for sure, in at one point of time, you can either go to at max 2 of these conditions because of the coordinate, how the coordinates works. It's either x or y. Now, as we mentioned that if we are at the borders, we can simply say that whatsoever is the number of ways I can reach here, that many number of ways I can also go out. So I can simply add these values. Again, that's not a if else, that's a if conditions, because you remembered I can also go out when my x, let's say this was the matrix. So you saw that my I is a 0 and my j is also a 0, which will contribute going outside. Contribute, so I is 0, j is 0, both contributing outside, going outside. Cool. Now when I have contributed the answer which I could have, considering I could have reached here these many number of ways, I have to propagate the answer to my child also, and I simply will say to my child that bro listen, that if I, like, this is my child, which will have the next move. So I will say to my child, bro listen, that one thing, you can reach, again my child, let's say I am at this state, this specific state. Now I am this state. Now my child is this, let's say he's pink, baby pink. Now I will tell him that bro, can you please find the answer for you? And again, I'm finding his answer, which means his next state, which means the next move for him, because he will actually be utilized in the next move. So his answer, my child answer will be calculated from top, left, bottom, right. This will be my child answer. So what I did was, again, there are 2 ways to implement it. One is that, okay, you keep contributing the current value, which means your parent answer to all the childs, or you see, okay, let's imagine this as a child, which is the pink child, and get in the answer from all the possible parents. So all the possible parents, you get the answer, and then when you have got the answer for this specific child, this will be used next time as a parent. So here I'm just using this specific way. Again, this specific way will also work, that for a parent, keep on contributing to all of its child, and same way, let's say for him as a parent, he will contribute this to his child. Same way it will happen, both are actually same, it's just an implementation way different. Now coming on back, that I'll just say that for my child, get all the possible parent values. Again, you will see that's a move plus 1, and I'm doing a move, which means this is the current value, this is my child, which is the upcoming. Child is nothing but who is coming next, and move plus 1 will be coming next, because you saw I am going on the move. So move plus 1 will be coming next, which is my child for sure. So I will just add all these possible values, and again, you can only add when you have a valid index. That's how a matrix work. Again, you can also put a border matrix, like usually how we, if you don't want to deal with these edge cases, what we do is we just put in a like border matrix. Okay, I'll put a 0 0 0 0 0, but yeah, if you don't want it, then simply skip it. But what will happen with this is, I am asking x minus 1 comma y, I am asking x plus 1 comma y, I am asking x comma y minus 1, I am asking x comma y plus 1, and ultimately this is my parent and this is my child. And that's how I can simply add the number of ways to reach to my child, because this number of ways to reach to my child will, again, let's say to reach to this specific child, number of ways were 3. So now to actually contribute to my answer, which means the path which goes outside, here you will see I can only go out only in one direction. So rather than only in one direction, that I know, but I will add a 3 as just specific this direction. And maybe if it was possible to go, let's say if this would have been the child, and next time he would have come in, and let's say for him the value would have been 3, that in 3 ways I can come at this point. So I would have added 3 here and 3 here as a number of ways. So my dp value is contributed as the path count. You will see my DP value is contributed as a path count. I'm adding answer. I'm not doing answer plus 1. I'm doing answer plus my DP value, which means number of ways to reach at that point. And from that point, I can go out. Okay, I can go out. And again, at max, I can go out in at most 2 directions. And that's how I can simply get the answer. This will be the code. As simple as that. Again, people will not teach this, hands down they will not, because it's a very tricky problem. But again, that's a risky state. That's a risky part which you do, that you should not touch these kind of things, which is 3D DP bottom optimization. People might not. And again, if you're confused, because there's a high chance, if you're confused, it's your first 3D DP optimization problem or 3D DP bottom up problem, then I'll highly say please go back and watch the video again. Now simply you can very visually see the improvisation, that for just move plus 1, I'm only using my move, as we have seen previously also, that okay, for DP of x comma y plus 1, y plus 1, I'm only using DP of x comma y. If that happens, okay, I can actually replace this with 2 vectors. So now I can replace this entire thing with 2 2D vectors. So I can just say that this DP, let's name it as a next DP, and this DP is nothing but the DP itself, because you saw it's a move plus 1, which is the child DP or the next DP, which is upcoming DP. So I'll name this as a next DP, and this is the DP itself. So rather than having a 3D DP, I will have 2 2D DPs, saying one DP will be nothing but the DP itself, and other DP will be the next DP. You can also name it as a child DP, next DP, or you can also name it as a child DP. With this, simply I'll just replace the entire thing. It will not be there, 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 not be there, not be there. And yeah, that's it. That's the only difference which I will do. And thus one difference is I'll also remove this, and I only have DP. I will also have a next DP being initialized. That's the only change I have to do to actually improvise that. So you will see I initialized my DP and next DP, and I changed all of these variables I mentioned. It became next DP, and all these became my DP, and I removed the move variable because I know the next DP is the next DP and this is the DP itself. With this, you saw the time will still remain same, but the space is now reduced, and that's how you can actually optimize it. I hope that you got this. Goodbye, take care, bye bye, and please make sure that this is again not a medium problem, considering you go on to the improvised bottom-up DP approach. Bye bye.